shall continue talking about Landau damping and growth of waves in plasmas. We shall discuss Landau damping of a plasma wave, then Landau damping of ion acoustic wave, bump in tail instability and ion acoustic instability. The references for today's talk would be 3 books, one by Stix, another one by Kroll in treble piece, and third one by F.F. Chen. Let me recapitulate what we were doing last time. We were considering the response of a plasma to a wave of potential phi is equal to A exponential minus I omega t minus kz. And what we had done was that we said that in the presence of this, the distribution function of electrons can be written as F0 plus F1. F0 is the equilibrium distribution function and F1 is the modification caused by the plasma wave of potential phi. Then we solved the Vlasov equation for F1 and we obtained an expression for the perturbed distribution function, which was is equal to E k phi divided by m omega minus k v z multiplied by delta F0 by delta Vz. Here minus E is the electron charge and m is the electron mass. One may note here that those particles for which Vz is equal to omega upon k, the denominator will go to 0 and they are called the resonant particles. The perturbation in F1 will be very large. And these are the particles which give rise to resonant wave particle interaction and are responsible for damping or growth of waves. Then we introduced the density perturbation, which essentially is a triple volume integral of F. This F1 into dVx, dVy and dVz. At this stage we introduced a quantity called one dimensional distribution function, because when you integrate this F1 with respect to Vx and Vy, well, the derivative of F0 comes only through Vz and there is no Vz dependence here, no Vx and Vy dependence here. So, this can be easily integrated and one introduced a quantity called one dimensional distribution function F0, which was essentially double integral of F0 over dVx and dVy. So, this F0 is a function primarily of Vz, only of Vz rather. And in terms of this, one can obtain N1 and we said that I will write N1 as k square epsilon 0 upon E into chi into phi. Epsilon 0 is called free space permittivity and chi is called the susceptibility. Let me put a subscript E. I think we put a subscript E because this designates electron susceptibility. And the expression for chi E then is equal to minus E square upon m epsilon 0 k square integral minus infinity to infinity delta F0 by delta Vz divided by Vz minus omega by k, and this was dVz already I have written. Sorry, dVz I have to write dVz. This is the expression we had written last time, And for the case of Maxwellian distribution function, Maxwellian distribution means I choose F0 as density of electrons per unit volume divided by pi to the power 1 half multiplied by V thermal into exponential minus Vz square by V thermal square. So, for this case we found that susceptibility becomes simple, is expressible in terms of z functions, and z function I defined as z of xi is equal to 1 upon root pi. This goes from minus infinity to infinity exponential minus p square upon p minus xi dp. And the evaluation of this integral has to be done following the Landau's prescription. So, what we do here, if I plot real Vz we treat or P we treat as a complex quantity. So, real part of P we plot here and imaginary part of P we plot here, and then we carry out the integral along the horizontal axis, because there is a pole at xi. So, this is the pole at xi, but the integral has to be like this, it has to go around the pole. So, this is the integral, line integral. So, following Landau's prescription, one can evaluate this integral, and people have indeed evaluated this integral. Fried and Contd have carried out this study. G function always has a contribution due to this pole, and in the limit when xi is much bigger than 1, this becomes, this z function of xi is approximately equal to minus 1 upon xi minus 1 upon 2 xi cube minus 3 upon 4 xi to the power 5 plus I root pi into exponential minus xi square. This is the expression for xi in the limit when xi is much bigger than 1, and in the other limit when xi is much less than 1, you can write z approximately equal to minus 2 xi etc. plus I root pi exponential minus xi square, and this factor is nearly 1. So, this is like I root pi. Well, in terms of this z function, the plasma susceptibility was, susceptibility chi e we had written was, is equal to 2 omega p square upon k square V thermal square 1 plus omega upon k V thermal into z function of omega upon k V thermal and the dispersion relation was for the plasma wave 1 plus chi e is equal to 0. Now, I would like to simplify this by presuming that the phase velocity of the wave is bigger than V thermal. So, omega by k V thermal is greater than 1. Xi implies here is the argument of z function, which is omega by k V thermal. So, well, let me mention here that xi I am talking about is omega upon k V thermal. So, in the limit when omega by k V thermal is bigger than 1, I can use this expansion, and when I carry out this expansion, chi e turns out to be rather simple. Let me write down this expression. or rather this expression I will write down. So, if I write this, this takes the following form: 1 minus omega p square by omega square minus omega p square by omega square into 3 by 2 k square v thermal square upon omega square plus the imaginary part I root pi omega 2 omega p square divided by k square v thermal square into exponential minus omega square by k square v thermal square is equal to 0. I forgot to mention that V thermal is related to electron temperature by this relation 2 Te upon m, where T is the electron temperature, m is the electron mass. Well, if omega is substantially bigger than kV thermal, this term is quite small, but is still significant. So, this is a equation which you can solve for omega, and I can write down omega is equal to a real part of omega plus imaginary part of omega, but this turns out to be negative. So, I will write down simply minus here into gamma, and presuming that omega r is bigger than gamma, you can equate the real imaginary parts of this term to 0 separately. So, real part of omega turns out to be omega r turns out to be equal to omega p square, this is equal to this square plus 3 by 2 k square v thermal square. This, if you equate this equal to 0, you will get omega r actually, this expression you will get. And nearly approximately, because I am taking this term to be small as compared to this one. And imaginary part turns out to be gamma, which we call it the damping rate. It turns out to be root pi omega p square into omega divided by k, this should be k square v thermal square. Actually, this is cube here, and this is k cube v thermal cube multiplied by exponential minus omega square upon k square v thermal square. You may note here that the damping is a function of frequency. Frequency, this omega is omega r actually, but we can suppress the subscript r, implying that it is implicit. So, the frequency you may note here, if I plot omega r as a function of k, suppose omega p is here, at k equal to 0, omega equal to omega p, and if we plot here, this will go something like this. This sort of variation you will get. Now, if you are too close to omega p, then k will be very small, and when k is small, this quantity is very large, so damping rate will be negligible. So, if I plot here damping rate I will call as gamma as a function of k, because when k changes, omega correspondingly changes. So, use a proper value of omega from this graph and use this here, then plot gamma as a function of k. You will find that when k becomes comparable to omega by V thermal, in that case this term is nearly unity, and this is huge. So, damping rate is very tiny and becomes very large when K becomes comparable to omega p by V thermal. Suppose omega p by V thermal is here. This is omega p upon V thermal. I am varying this quantity K here. So, this is the point where omega K becomes omega p upon V thermal. The damping is very huge here. So, you start from here and then it increases rapidly. The scale for this is different than the scale for omega, but this could be quite large. Obviously, my approximation fails here. It is not valid up to this point, it is valid only up to somewhere here, because as I mentioned to you, I have already assumed that omega r is bigger than K square V thermal square. So, this was my assumption. So, I cannot go close to unity here. I should be maybe half or something, 1/3. So, but still the damping is strong as you move to shorter wavelength or larger values of K. And this is a collisionless damping. It will be useful to look at the wave number or phase velocity of the wave over the distribution function. If I plot here f0 as a function of Vz for a Maxwellian plasma, this goes like this. This is my Maxwellian distribution function, and my thermal velocity is somewhere here. This is my thermal velocity somewhere here, and my phase velocity of the wave is somewhere here. So, suppose my omega by K is here, depending on the value of K. These are the particles which are called resonant particles. So, in this neighborhood you are expecting resonant interaction of waves with particles. This is the range. What will happen? The particles which are on the left of this omega by K point, these particles are moving slower than the wave. The particles which are ahead of it, they are moving faster initially. But as I mentioned that as the wave grows, these particles lose energy, the faster particles lose energy and the slower particles gain energy. Consequently, the particles from here to here move and there is a plateau created there. So, the distribution function appears becomes like this. f0 if I plot Vz here, the distribution function I have plotted here. So, in this some plateau is created here. This is the range Vg is omega by K is here. So, a plateau is created, horizontal becomes flat. Once this becomes flat, then there is no growth because there is no slope in f0. So, Landau damping will be a transient phenomenon. After a little while, when this flattens, there will be no damping. Obviously, if the electron-electron collisions restore the distribution function to be Maxwellian, then this will be an ongoing process. So, Langmuir waves will damp up to a point, and beyond that point the damping will stop when the particle distribution function has become like this, until or unless there is a restoration of Maxwellian form of the distribution function, which collisions do. So, this is some physics we have learned. Obviously, the waves of larger K, this omega by K point will be closer here, and then the number of particles in the distribution function are more. So, there are more and more resonant particles and there will be stronger damping. So, when omega by K is very large, when K is very tiny, then there is hardly any particles and there is very little damping of the waves. So, one can see this. Now, let me examine the ion acoustic wave in the presence with kinetic effects. So, ion acoustic wave from fluid theory we had learned that this is a wave of frequency omega is equal to K Cs upon 1 plus K square Cs square upon omega pi square to the power half. where Cs is under root of Te upon Mi, where Mi is the ion mass and omega pi is the ion plasma frequency, which is defined as N0 E square upon Mi epsilon 0 under the root. So, a wave of frequency omega with wave number k will have a phase velocity omega by k which is less than Cs, depends on how close Kcs is to omega pi, but the highest value of omega is less than omega pi. So, if I plot a graph here, omega versus Kcs, and suppose omega pi is here, then this goes like this, it saturates. But please remember, in the case of ionoacoustic wave, the velocity is much less than the electron thermal velocity, 50, 60 times or 100 times smaller. However, the ion velocity may be comparable to the velocity of the wave, especially if my k is large, then omega by k could be significantly smaller as compared to Cs. When Kcs becomes comparable to omega pi, there is a significant reduction. So, the phase velocity of this wave V phase, which is defined as omega by k, is less than Cs because there is a factor underneath. So, it is possible that larger k waves will have a thermal velocity comparable to ion thermal velocity. Oh, because the velocity is, if Te is Ti are same, then thermal velocity will be comparable to Cs and the wave will be strongly damped. So, here the damping is expected to come from the ions. So, what you do, you look at the same expression for, as we had seen for the electron susceptibility, you can write down the expression for ion susceptibility. Electron susceptibility we had written was 2 omega p square upon k square V thermal square 1 plus omega upon k V thermal of electrons, plasma dispersion function of omega upon k V thermal. But we are considering the limit when omega is much less than k V thermal, then this quantity is negligible. So, this is primarily equal to 2 omega p square upon k square V thermal square, and this you can easily see is equal to omega pi square over exactly same as k square Cs square, because omega pi square contains a mass 1 upon mass, V thermal square also contains 1 upon mass, and they cancel out. So, whether you put omega p, omega pi or Cs, the same thing happens. So, this is the value of chi e. How about the ion susceptibility? Ion susceptibility chi I is by similarity 2 omega pi square, where omega pi is the ion plasma frequency, upon k square V thermal ion square, and then this becomes 1 plus omega upon k V thermal of ions Z function of omega upon k V thermal of ions. Here I am assuming the plasma to be Maxwellian. This term again here for sound waves we are expecting omega upon k V thermal of ions to be bigger than 1. So, in the large amplitude approximation I can expand this plasma dispersion function Z function, and in that case chi I turns out to be approximately equal to minus omega pi square upon omega square, that is nearly the real part, and imaginary part simply is equal to plus 2 omega pi square upon K square V thermal square into I root pi. So, I will put here I root pi omega upon K V thermal of ions and exponential minus omega square by K square V thermal ion square. Well, so chi has, this is the ion susceptibility, it is not the imaginary part, this is the real part and the imaginary part. Real part of this and chi E will determine the real frequency, and this will give rise to damping of the wave. So, let me write down the dispersion relation. The dispersion relation for the sound wave is 1 plus chi E plus chi I equal to 0. Chi I essentially is characterizing the perturbation in the electron density when you multiply this chi E by phi, and this characterizes the modification in the or perturbation in the ion density by the wave. And wave we are considering like this, A exponential minus I omega t minus k z. So, this is the dispersion relation for the sound wave or ion acoustic wave, and this turns out to be 1 plus omega pi square upon omega k square Cs square. This is the electron susceptibility, and ion susceptibility is omega pi square upon omega square plus I root pi, and then you get 2 omega pi square upon k square V thermal I square omega upon k V thermal I multiplied by exponential minus omega square upon k square V thermal I square. The real is equal to 0. If I forget this, I get the real part of frequency from here. But when this is included, I can write down omega is equal to omega real minus I times some damping rate. Omega r, just when you obtain from here, is the same as I had given before by fluid theory, but this is the additional term that you get because of damping due to ions. So, let me write down the explicit expressions for omega r and the damping rate. Omega r is k C s upon under root 1 plus k square C s square upon omega pi square, and damping rate turns out to be root pi. It turns out to be, I guess, omega 4 upon k cube V thermal I cube exponential minus omega square by k square V thermal I square. This is called ion damping. So, your phi, the amplitude of the wave phi modulus, if you plot, will go as exponential minus gamma t. So, it will damp out. Now, if I plot the distribution functions for electrons and ions, what I will get is this. If I plot here Vz and put the distribution function for electrons and ions separately, the ion distribution function will be like this. let me draw by a different color. The ion distribution function will be like this. And the electron distribution function will be like this. Let me by different color. And my wave velocity is somewhere here. Omega by k is somewhere here. So, the slope of the electron distribution function is very tiny, and that does not give rise to any damping of waves. But it is the slope of the ion distribution function, this is ions and these are electrons. I am plotting here F0 versus Vz. So, these are the ions here which are responsible for the damping of the wave. It is very important to note that, because especially when you are talking of wave frequency less than omega pi. So, when omega is significantly less than omega pi, maybe 1/3 or less, then omega is around kcs, and this is the factor here which is responsible for damping. It can become quite large. The damping rate turns out to be, for low frequency wave, gamma is of the order of root pi omega Te upon 2 Ti cube exponential minus Te upon 2 Ti. This is very important. This tells that unless Te is much bigger than 2 Ti, there will be very strong Landau damping of ion acoustic waves. So, Te must be much bigger than 2 Ti for weak damping of these waves. A plasma in which temperature of electrons is much bigger than the ion temperature is called non-isothermal plasma, non-isothermal plasma. But certainly there are plasmas in which temperature of ions is much less than the electron temperature, and the ion waves are quite weakly damped. Well, this argument is true when we are talking plasmas with singly ionized ions. In plasmas where ions are doubly ionized, or they have charge 2e or 3 or 4e, then this condition changes. But those details are not relevant at the moment. I just wanted to emphasize that thermal effects cause damping of waves. However, with a suitable distribution function, they can give rise to instabilities as well. Physically, where would you expect instability? A simple example is the case of a bump in tail distribution. I think I will write this on a separate sheet. Let me talk about the bump in tail distribution, and the instability or the growth of the wave arising because of that is called bump in tail instability. Bump in tail distribution. Function. So, suppose we have a plasma which has a distribution like this. I call F0, suppose as a function of Vz. If I plot, I get this kind of thing, and this goes like this. So, there is a bump in the tail of the distribution function, and in case your wave phase velocity were lying somewhere here, the slope is positive here, and the wave velocity, the wave that you are considering, has a phase velocity somewhere here, then the slope is positive and the imaginary part of omega will be positive, and that will give rise to growth of the wave. because here the number of particles moving faster than omega by k are more and the particles moving slower than omega by k are less. So, more particles are moving faster than the wave and they will give energy to the wave, so wave will grow. This kind of distribution you can easily write down as a sum of a Maxwellian distribution and a drifting Maxwellian distribution. So, I can write down this F0 is equal to Maxwellian distribution plus drifting Maxwellian. And so, I can write down Maxwellian, I will write down simply F0 m plus F0, the drifting Maxwellian I will call F0 b, maybe something sort of a drifting particles or beam particles moving. Actually, I can call this actually F0 either m or F0 p, the bulk plasma particles. So, bulk of the plasma electrons are having Maxwellian distribution and some particles are moving with drifting Maxwellian. So, let me write down these expressions. Maxwellian distribution function in one dimension I can write down as n0 upon pi to the power half into thermal velocity of the plasma electrons exponential minus Vz square upon V thermal square. So, these are my electrons of the bulk electrons of the plasma, but there are some tail electrons, I will call them F0b. Suppose this is equal to n0 upon pi to the power half. Their thermal spread of energy of velocity is suppose less, V thermal b is the thermal spread exponential minus Vz minus V0b square divided by V thermal b square. So, I am writing two distribution functions, sum of two. This is Maxwellian from here to here, this has a peak at Vz equal to 0, but this has a peak at Vz is equal to V0b. So, the distance of the peak from this point is V0b, and V thermal b is called the, I can write down V thermal b, thermal velocity of beam electrons or drifting electrons, which I can define as 2 temperature of the beam electrons upon mass of the beam electrons, and V thermal is 2 Te upon m, but Te and Tb could be very different. So, this is the beam part, this is the bulk part, bulk electrons or plasma electrons. If I use this in the original expression for density perturbation, you get the density perturbations, and I can define two quantities. Susceptibility of the electrons turns out to be one comprising the Maxwellian part contribution plus one having the beam contribution or drifting Maxwellian contribution. There are two susceptibilities. Obviously, density perturbation of the whole system is k square epsilon 0 upon E into susceptibility of the electrons into phi. So, this chi is a very important quantity. Now, this has a sum of two terms, one from Maxwellian electrons and one from drifting Maxwellian electrons called beam electrons. And what happens if you work out little bit, just follow the old procedure. Chi m is the same expression as before, which is 2 omega p square divided by k square V thermal A square into 1 plus omega upon k V thermal, z function of omega upon k V thermal, whereas chi m becomes chi b is different. This is twice omega p b square. I may forgot to mention that the density of electrons that I had written earlier, the drifting electrons may have a different density. I will call it N0b. So, if I take this density N0b, then the corresponding plasma frequency will be omega Pb upon k square V thermal of the beam electrons square 1 plus omega upon k. This turns out to be omega minus k V0b upon k V thermal of the beam. This is the modification. Here is omega only, and this is omega minus k V0b, which is called Doppler shifted frequency of the wave as seen by the particles. And this is omega minus k V0b upon k V thermal. So, the total susceptibility of electrons has two terms. One has an important term with Doppler shifted frequency, and the other one has just a frequency omega. What you can do for the instability, you are certainly looking for a case where beam velocity is more than or comparable to omega by k, but this is much bigger than V thermal of electrons or V thermal of the beam electrons. That is the case of interest. So, in that limit, this simplifies a great deal. It becomes of the order of minus omega p square by omega square, simply this term. And well, actually let me define omega pb here. This is the important quantity. Omega pb is I have defined as N0b, the drifting electron density, E square upon m epsilon 0 under the root. Please note that in this limit, when the beam velocity is much bigger than the thermal velocity of electrons, or the thermal velocity spread of the beam distribution function, in that case I can simplify these two expressions a great deal. So, chi m turns out to be simply this: chi b will have a real part plus a imaginary part. The real part will be small as compared to the real part of chi m, because if the density of beam electrons is small, then I expect this to be a small modification, but the major contribution will come in the imaginary part. So, this is what I am going to do here. I am going to write this imaginary part of this term, and my dispersion relation is 1 plus chi m plus chi b is equal to 0, and when you substitute, this becomes 1 minus omega p square by omega square due to the second term, and chi b I will simply write only primarily imaginary term, which is equal to plus 2 omega p b square upon k square V thermal beam velocity square into I root pi omega minus k V0b upon k V thermal of the beam into exponential minus omega minus k V0b square upon V thermal square multiplied by k square. This is B. This is equal to 0. So, this imaginary part, because there is a small, well, I have written in the limit when beam density N0B is significantly less than the plasma density. In that case, real part of the beam contribution to susceptibility can be ignored as compared to the real part of the electron plasma electron contribution. So, if I ignore this, I get omega equal to omega p, but because of this term omega I can write down as omega p minus or plus rather I times growth rate. Just substitute it here and equate the real and imaginary parts, you will get the growth rate. So, growth rate turns out to be equal to, let me just write down this expression, it turns out to be root pi into V0B minus omega by k upon V thermal of the beam, thermal spread in velocity of the electron beam, into omega Pb square upon k square V thermal beam square exponential minus V0 beam minus omega by k whole square divided by V thermal beam square. So, whenever the beam velocity is faster than the phase velocity of the wave, more electrons are moving faster than the wave, and hence they feed energy into the wave and wave grows. So, this is the growth of the plasma wave at the expense of energy of the electrons in the tail. So, whenever there is a bump in the tail, whenever there is a positive slope in the distribution function, you will get this instability. So, plasma waves are often driven unstable whenever there is a stream of particles moving faster than the thermal velocity of electrons, plasma electrons, and they create a bump in tail and you get instability. This is a very important instability in plasmas. I would also like to talk to you about another instability. You can drive the ion acoustic waves also unstable by an electron current. So, let me just mention finally current driven ion acoustic wave. Or simply ion acoustic instability. This system is rather simple. If you take a plasma somewhere and put two electrodes to which you can certainly apply a potential difference, pass a current in the plasma. The distribution function, and there is a pump here, so that you can create a vacuum. So, when you have a plasma at low pressure or gas filled in it at a low pressure and you create a discharge, you produce a plasma, but the plasma electrons also have a drift, they are drifting towards the anode, and the distribution function can be reasonably taken to be Maxwellian, drifting Maxwellian. So, if I take the plasma electron distribution function like density of electrons pi to the power 3 by 2 V thermal cube exponential minus V minus, suppose the electrons are drifting with drift velocity V0 in the z direction upon V thermal square. So, this is the distribution function. Then if you work out the, and ion distribution function usually in such plasmas can be taken to be F0 of ions as N0 upon pi to the power 3 half V thermal of ions cube exponential minus V cube upon V thermal cube of this is the distribution function of ions, this is I, V thermal I. In that case, the distribution functions will look like this. If I plot here the distribution function for electrons, the electron distribution function will not have a peak here, it has a peak at V equal to, so if I plot this as a function of Vz, and F0 here, the distribution function for electrons will be like this. So, the peak of the distribution function is somewhere here. So, if I have my omega by k just below the peak, here this peak is shifted at distance V0, the distance from here to here is V0. So, for V0 greater than omega by k, the slope of the electron distribution function is positive. So, there are more electrons moving faster than the wave and fewer moving slower than the wave, and there will be instability. Mathematics is trivial for this case. Just let me write down. We are having the dispersion relation 1 plus electron susceptibility plus ion susceptibility equal to 0, and the electron contribution turns out to be chi e, which is 2 omega p square upon k square V thermal square into 1 plus omega minus k V 0 upon k V thermal of the plasma electrons into z function of omega minus k V 0 upon k V thermal. Since for sound waves k V thermal is too huge as compared to omega or omega minus k V 0, too huge. So, this quantity, real part of this quantity is negligible, imaginary part, so this becomes approximately equal to, this becomes equal to omega pi square upon k square V thermal Cs square, and this becomes 1 plus I root pi into omega minus k V 0 upon k V thermal. And if I take ions to be cold, so in the limit when Te is much bigger than 2 Ti, ion susceptibility is nearly equal to minus omega pi square by omega square, so that the ion damping can be ignored. So, in that limit, if I just substitute this chi e here and chi I here, you will get instability whenever V0 is more than omega by k, and it is very trivial to get the dispersion relation. You will get here the dispersion relation will have omega is equal to omega real plus I gamma. Omega real is the same as you obtain from the fluid theory, the real frequency of a sound wave, which is kcs upon 1 plus k square cs square upon omega pi square under root, and the growth rate gamma turns out to be equal to root pi omega cube upon 2k square c square into omega minus, sorry, this is V0 minus omega by k upon thermal velocity of electrons. As I mentioned, omega by k is like Cs, V0 has to be slightly more than Cs. So, this quantity is quite small, but significant. So, whenever omega is of the order of kcs, growth rate is comparable to omega into this ratio V0 minus omega by k upon V thermal, or this is like Cs. So, this is maybe I would say like 1/50th, but it is still quite significant. So, this is, let me write this as omega into V0 minus sound velocity upon thermal velocity of electrons. So, this is still significant. So, sound waves have been found to be generated in plasmas carrying currents. Even simple discharges will produce plasma waves, sound waves. Sound waves are like acoustical phonons in solids. In a solid, whenever the sound waves travel, we say that acoustical phonons exist. So, whenever you apply a DC electric field to a conductor, the electrons when they drift, they suffer collisions with phonons and that gives rise to resistivity. Similarly, in plasmas, if you pass a current in a plasma and sound waves are generated, then these waves can also give rise to plasma resistivity, which could be significantly higher than the resistivity due to particle collisions, electron ion collisions or electron neutral collisions. And I think in our next lecture we shall talk about the effect of such instabilities on resistivity. I think I would like to stop at this stage. Thank you.